Hi, so this is our Comp 481 final project report of Project 1 and Project 2. Our group members are Cameron, Manbeer, Bulgar, Michael, and Gurveer. So this is our Project 1, our e-commerce transaction analyzer in Haskell. And the goal of this project was to build a small tool that can track online purchases and help a user understand where their money is going. We had three main objectives: to store each purchase as structured data, to let the user filter transactions by category or by minimum dollar amount, and calculate the total spending per category. To do that, we defined a custom transaction record in Haskell that keeps a date, category, amount, and a short note for each purchase. And then we wrote the two main filter functions: filter by category, which selects the transactions by category, and filter by minimum amount, which selects only transactions above a chosen amount. And both of these reuse Haskell's built-in filter as a higher order function, so they can easily be chained together. And then lastly, we implemented total by category, which first sorts and groups the transactions by category and then uses a strict left fold to sum the amounts for each group. And then we outputted it in this format you see on the right.
With slide 4, continuing on, we had some key technical highlights for our project, our transaction analyzer in Haskell. One of the main strengths of our implementation was we used pipelines to process our data. Instead of nesting a bunch of functions inside of each other, we apply them step by step. First we filter, then we sort, then we group. Makes the program read like a clear sequence of actions, which is easier to follow. This also ties into why order of operations matters so much in Haskell. For example, we first have to sort before we group, because group by only works correctly if equal items are next to each other. And then we need to filter before we total things up, otherwise our totals come out wrong. The pipeline structure makes that ordering obvious. Performance-wise, we used fold L hyphen instead of the lazy fold L version, so the program doesn't build up large chunks in memory. And throughout the project, like you were asking about, we used lambda functions, especially inside our filters and our folds, to express quick pieces of logic like /t to category t equals cat. Keeps the code compact while also being readable. We also relied on type safety when defining our proper transaction record data type, and we use functions like sort by, group by, and sum to compute totals. And finally, we also use printf formatting so that the output tables are nice and easy to read. And here in slide 5, we did run into a few challenges. One of those was handling edge cases in filtering. What if, for example, the user picks a category that has no matching transaction records, or if the minimum amount you've put in excludes all transactions? We have to make sure we actually get sensible outputs in these edge cases, as opposed to having the program crash or produce empty or otherwise misleading outputs. One challenge was making sure the pipeline steps were ordered correctly. Even one step out of place, for example, grouping before sorting, completely changes the result. So we had to make sure this got the sequence right. Also, designing the transaction data type in a way that works with the higher order functions we were using. Any changes we made have to be reflected in those higher order functions as well, so we had to be careful about that. And also when dealing with lambda functions, as you were asking about as well, yeah, they're good when it's just small stuff, but if they get too long, it becomes quite complex and hurts the readability. And in cases like that, we move them into helper named function instead, so that the intent is clear, the code is easier to maintain. And also when using sort by, group by, and fold L hyphen, we can run into type errors when we have the data formatted wrongly, because they expect the data to be shaped a certain way. And of course, we had issues with imports and formatting, making sure we had the right modules load, otherwise the compiler throws errors, and then tweaking the printf output so that the table looks tidy. And overall, the project was really good to give us a clear understanding for how Haskell uses pipelines, ordering, and higher functions to produce logical results. And moving on to project 2, my teammate here will take over. Thank you.
This brings us to our second project, a knowledge base and reasoning system in Prolog. The objective we chose for this project is to incorporate knowledge and algorithm solutions for 3 independent domains. Each project section is split into 3 domains: commute, work, and personal. Each area has a facts and rule definition, utilities for helpful predicates, and a pre-made testing file for quick validation and testing. ARM implementations implement algorithms to solve different tasks and problems. The first implementation illustrates an example with recursion for pathfinding and dependency calculations. The second implementation shows constraint logic through an example work distribution. Finally, the third implementation shows a shortest path calculation algorithm.
From here on, I'll be taking over for the presentation. Here I'll be explaining how we implemented the shortest path algorithm in Prolog and its elements. So the algorithm basically needs two pieces of information, which is the starting city and which is the destination city. For example, we can take care, for example, the starting city would be Surrey and destination city would be Vancouver. We could have three paths which could be from Surrey, Richmond and Vancouver. Then we have Surrey, Burnaby and Vancouver, and then we could have Surrey, Coquitlam and Vancouver. So if we take that example, we have three paths, and then we use a find all predicate which has the distance pair, which is having a D for distance and pair, P for path, which is the pair. For routes, it stores the starting and the destination city with the path itself, and when it calculates the distance for each path, it stores in the PD value format. The routes are the collection of all distance path pairs. Here, for example, we have 120 as the distance and ABC as the path pair, and then we have two other along with 150 and 200. We use sort key predicate to arrange all the distant path pairs in ascending order, so the shortest comes the first, and finally it picks up the winner, which is the shortest distance. So in our case, it's the first element, which is 120 as the distance and path with ABC, and rest it gets ignored with the underscore, which means it is all other paths are being ignored. In this slide, I would be explaining the time versus dependency for our project. In this case, we can take a real world example for project really exists in isolation. So which means one task depends on another, which depends on the third task. So this basically explains the Prolog calculation method for total time needed when we have cascading dependency. So it takes in the input for one project, returns the total time needed including all dependencies, and what it does is it calculates the dependency chain. So the algorithm gets the deadline of the main project, checks if the project depends on another project, and here we have an example of the example chain, which is for project alpha depends upon project beta, and project beta depends upon delta, and delta doesn't have any dependency. What we can see is you can't start alpha until beta is done, so you can't start beta until delta is done. So we have a recursive summing which add all the deadlines over here, which adds, like for project alpha it has 10, beta it has 20, and delta is 30, which adds up to total of 60. With that recursive function, it continues and returns the sum of all deadlines in the dependency chain. This is the total time to complete the project with all its prerequisites. So in this slide, I'll be explaining the chore fairness algorithm, which is a constraint satisfaction algorithm that assigns chores to the people fairly. So just imagine that you are a parent with four kids and four household chores are there. Everyone needs to do one chore, and everyone must be able to do their assigned chores, and no more chores get be repeated twice. So what it does, it takes in the input, takes the list of people and list of chores, returns an assignment list where each person is matched with exactly one chore, and what it does is next it does a compatibility verification. It checks for each person to choose a chore from their available list, and then it verifies whether they can do it. And once it verifies, it does a pair style connection with the it has one person's names, for example Maggie, it can do laundry. So once it has the compatibility, it does that, assigns it, and it's done, and then it gets removed from the list so it doesn't get repeated. Once it's done, it selects the next chore for the available person, and next is like Part can do dishes. So dishes get selected and then it gets removed from the chores list. Finally, we have a recursion continuing until all the people gets their chore, and we produce a complete assignment list with no duplicates, and it helps to make sure it has a chore fairness quality. For this section, I'll quickly go through the experience and challenges we had during building the project too. So for the first one is understanding the difference between declarative language. Uh, the main difference is we have been traditionally programming in the imperative languages, which is like Python, Java, where you tell computer how to do something step by step using for loop and if else conditions. But Prolog is a declarative language where you tell to the computer what you want and it figures out how you need to do it. So that was a significant mental shift to stop thinking about loops and condition and start thinking about logic and relationship. Then we have building recursive rules. So the challenges was mastering recursive in logic programming. Common mistakes we had was forgetting the base case, infinite loop, and then wrong termination condition, and then getting wrong results. These were the things which we faced during challenges. And then we have backtracking, which is like one of the things when Prolog hits a dead end, it automatically goes back and tries an alternative solution, uh, which is important. And one path fails, it backtracks to choice point and tries another path. That was one of the things. And challenges was we don't keep in mind the performance that affects during backtracking. So we need to make sure that we implement Prolog to find solutions efficiently. And then we have the knowledge base. So in the knowledge base we have facts and rules which needs to be have a great data organization, redundancy and consistency with completeness. So that was one of the things. Handling constraints was one of the challenge, which was defining proper chores with compatibility, then having a path that is also efficient. That was part of handling constraint, and we actually were able to build it properly. Second one and the last one we have is the backtracking versus collection. In backtracking, as I already mentioned, that it goes back and searches for another solution. But in terms of collection, we have a method for solution, a bunch of different methods, like for example find all predicate keeps all the routes in one place, and then we decide from based on ascending order and then ignore the rest. So these were the things which we had in our experience and challenges. So here we have the conclusion of our projects. So for the project one, we basically focused on Haskell, emphasizing type safety, functional composition, and performance awareness, list processing. For project 2, on the other hand, we have Prolog with emphasized declarative modeling, recursion, and search. Both projects showed that many problems reduce to operate over list and graph. We saw that the trade-off of between different languages, whether it was Haskell and then going back to Prolog. Haskell gives strong compile time guarantees, while Prolog makes it easier to express complex logic and constraint, but can be harder when predicting performance. Basically, going through backtracking and recursion is different from Haskell and Prolog.